That's perfect.
And choose the Logitech mic.
Oh, I didn't realize you hadn't done that. I can help. Yeah. I thought we had done. I thought the echo, that's fine, and then this should be this one, extra. So now we have echo.
Always Logitech.
Yeah, we have the Logitech here, and we have the extra here.
No, the first one.
Oh, this one.
Yes.
This one.
Okay. Sorry.
So, all good right now? What?
Can you ask Pascal to confirm if
Yes, we hear you.
you don't need the microphone?
Yes.
Yes, yes, we hear you.
Can you hear me?
Yes.
Okay.
Okay, all right, so everything can be heard and seen now, good.
So, everyone can hear him speak? Because the microphone is just for the room.
Okay, oh, okay,
Oh,
yeah,
this is
it's good, good volume.
We
All
hear
right.
everybody.
So yeah, sorry anyone online who didn't hear the loud hurricane video earlier. So this is a study by Worsnop et al. Who looked at a large eddy simulation, and I'm going to use the same simulation in my work. And what they did is they showed that the 3-second gusts in Category 5 hurricanes can exceed 70 meters per second, which they looked at because that's a design threshold for some offshore wind turbines. And so in some of our work, we try to seek to better understand the frequency of these extreme wind gusts and to estimate quantitatively for the probability that a given location would encounter such a gust on both short and long time scales. And now I can't, okay, there it works. The specific questions I'm trying to answer are one, how strong does a tropical cyclone need to be in order to be capable of producing these extreme wind gusts near the surface? And second, during the passage of a single intense storm, what is the probability that we might encounter such a gust? And then I'm going to talk about trying to estimate over several decades or longer, what's the likelihood of a given location experiencing these wind gusts. And for that, I'll be using Jiang's CHAS model. And then finally, I'm going to talk a little bit about how might this change in the future climate. And then if there's any time, I might talk about a different topic for a few slides after that. So this is the large eddy simulation that we're looking at. First, this is the Category 5 simulation studied by Orsay et al. This simulation was done by George Bryan at NCAR. So this is uses the CM1 model, which if you're not familiar with is very similar to the WRF model, but optimized for idealized simulations. And so what I'm showing here is the eye wall of an intense small hurricane with a grid spacing of only 30 meters. So much smaller than what most people have been talking about so far in the last couple of weeks. So with 30-meter resolution, we can resolve these small-scale tornado-scale vortices in the eye wall. So you see this is the 10-meter winds, and the yellows are around 70 meters per second. So the mean winds are around that. But embedded within that area of yellow are all these little red blobs that are moving around and that you can track in time. And those represent winds of 90, 100 meters per second, even 120 meters per second. And importantly, they're there at all times, but they're very hard to observe. So in our 2018 paper, I looked more at the structure and evolution of these extreme wind gusts. And so on the left, this shows trajectories in horizontal space of these features that I objectively tracked following the updraft. And they, like the Warm Inikosiba observations, these features move around the eye wall at about the mean winds of 70 to 75 meters per second. And following the most intense feature here in magenta, we could track it for about 2 minutes. And the boxes on the right here show zoomed in 1 by 1 kilometer boxes showing the horizontal wind speed at 2 snapshots a minute and a half apart. And what you can see is the scale of these features is order 500 meters. The winds are in excess of 100 meters per second. I put in some other contours of vertical velocity and vertical velocity to show that these are coherent features that are associated with a vorticity maximum. And the vorticity maximum is co-located with a very strong updraft. So moving on to look at how quantifying the extreme wind gusts and how they vary with intensity. So I have 3 different simulations, representative roughly of a Category 1, 3, and 5 hurricane. On the left shows the maximum instantaneous wind speed over the 4 hours of this simulation. It's initialized from an axisymmetric simulation, and it very quickly spins up turbulence in 10 to 20 minutes, and then you get a quasi-steady state. But if you look at the red line, Category 5, we have peak instantaneous winds of 110 to 120 meters per second, which is very strong and seems like it might be too strong for even a Category 5. But that's because we're looking at the gusts that are a few seconds in scale, a few hundred meters in scale. But when we talk about TC intensity, we generally refer to some longer average. In the US, that would be a 1 minute average. And if we take the 1 minute average and look at the peak wind speed for the Category 5 storm, we get 75 to 80 meters per second, which is about 150 knots and is comparable to numerous observed Category 5 hurricanes. So this is a representative simulation, we think. So now we can look at cross sections of the wind speeds and look at the features in these different simulations. I'm looking from left to right for Category 1, 3, and 5. And for the next few slides, I've helpfully indicated which category with a photo of my cat. So the number of categories. But what we can see is 10-meter winds on the top, 100-meter winds on the bottom. And the key thing is that, I mean, the wind gusts increase with mean intensity as you would expect. But you see similar small scale features in the eye wall of all these 3 simulations. And for the category 3 and 5 storms, you have gusts that are well in excess of that 70 meter per second threshold that we were focusing on. So we want to quantify the peak wind gust that you would expect to see if you were in the path of this storm, as well as the probability that you would experience a gust exceeding thresholds like 70, 80, 90 meters per second. And so to do that, we can sample the simulation at these simulated towers spaced every kilometer horizontally, take 10 minutes of output that was saved every time step, and compute the expected value of the peak sample 3-second gust, as well as the percent of towers which exceeds a given wind speed threshold. This shows that for the 3 simulations, again, focusing on the bottom here, this shows as a function of radius and height and the lowest couple hundred meters, the absolute maximum wind gust over this 10-minute period for these simulations. And so what that would be is going back here, if we pick any given radius, we take all the towers at that radius and find the peak gust from any of those towers, and that's the peak. And so for the category 5, for example, we have one of those towers, a gust of 122 meters per second, which is very strong and could be observed, but probably wouldn't be observed because you'd have to be at that one unlucky location. So what's more representative is the azimuthal mean of those towers. And what you see is for the category 5, the expected value of the peak gust that you would sample or experience is about 110 meters per second. And for category 3, it's 80 meters per second. And both of those are very strong and in excess of what these wind turbines were designed for. So we would expect to sample winds of exceeding this threshold if we were in the path of these hurricanes. And we can compute the probability of exceeding that for the category 3 and 5 storms, because the category 1 doesn't have any gusts that strong. And these are for different thresholds for 70, 80, 90 meters per second. And you can see that the category 5 has a substantial radial region where all of these thresholds are seeded by every single tower in almost the entire lowest 200 meters. And the category 3 storm has a small area where you might expect, where you might be able to sample 90 and 80 meters per second gusts, and a several kilometer wide region where you would expect where nearly every tower samples 70 meters per second winds. So for a couple slides, I'm going to move back to observations, in part as a reality check on our simulation and also to gain some more insight into these features. So on the left, this shows observed dropsonde wind speeds versus best track intensity. So every blue dot is one of thousands of dropsondes, and it's the maximum sonde wind speeds in the lowest couple hundred meters versus the best track intensity at that time. There's lots of scatter, and you can't get much out of it because most of the points are not in the eye wall. So what's actually meaningful is to take the maximum over all sondes at a given best track intensity, and that gives you the peak sample gust as a function of intensity, and that's the black line. And so we see the peak observed wind gust increases linearly with the best track intensity. And importantly, it also corresponds approximately with simulated dropsondes that I have in the simulation, and we can randomly sample those. And because for small numbers of simulated sondes, it corresponds relatively well with the black curve there, and so we think that our simulation is reasonable. But it's also important to note that dropsondes, in reality and in the simulation, systematically undersample the true peak wind gust by a lot, and so, especially compared to if you were at a fixed point and the storm is moving over you. So this is an underestimate of what the true strength of the wind gust that you would encounter in a storm.
Dan?
Yeah.
Why undersample size in the simulation?
Because in if you look at like the true peak wind gust.
Can you repeat the question with a cube?
With a what?
The cube, so people online
Okay.
can hear it.
Okay, so Susanna was asking why you would undersample with a simulated dropsonde in the simulation. And the reason is that, so the true peak wind speed is shown in this plot on the left here. The peak 10-meter wind speed is the highest point anywhere in the storm at any grid point. But we're putting dropsondes in the simulation, and it's as if it were a real sonde, and it's just sampling a point, and it's being infected around horizontally while falling, and it lasts for a couple minutes. And so it samples like the boundary, the lowest couple hundred meters for 20 seconds or so. So it's both. So we're just taking a sample of like 10 or 100 random dropsondes. So you're going to just have small samples of the truth in the simulation. So the figure here on the right shows the frequency of eye wall drop-ons that exceed these wind speeds as a function of S-track intensity. So for every flight, I'm finding all the drop-ons in the eye wall and seeing how many of them sample these extreme wind gusts to see how frequent they are as a very rough estimate. And look just at the black line, which is the maximum overall flights at that intensity. And what this shows is that when you're less than a major hurricane, less than 100 knots, you never sample these 70 meter per second wind gusts, but it rises sharply to nearly 100% for a Category 5 hurricane. So from observations, nearly all the eye wall SONs in a Category 5 would sample this, which is comparable to what we see in the simulation. We can also take a look at simulated tower observations like the ones I was showing you a minute ago to compare it to real tower observations, even though we're not simulating this real storm. So this is the 10 meter wind speed from Hurricane Ian on the left over 6 hours here, 3-second winds in blue and 60-second 1 minute mean in red. And then we zoom in on this period in the box, this 10-minute period, and that's shown in the center here. For different averaging periods. And then on the right is a simulated tower in the LES, which has no correspondence to the tower in Ian. And so the wind speeds shown on the y-axis in the simulation and Ian are different, but the ranges are the same. So what you can see is that Hurricane Ian at landfall exhibited these wind speed fluctuations that are similar in timescale and amplitude to that seen in the LES that's valid for the open ocean. And so we think that these observed wind gusts in the eye wall are likely the result of the same type of vortices we see in LES and similar to what was seen from radar in Hurricane Harvey. And in future work, I'm hoping to be able to conduct more realistic LES for idealized TCs that make landfall in order to better quantify the risk of extreme wind gusts for landfalling storms. Moving on now to looking at the long-term risk, I worked with Juin to use Chaz model to try to say something about over many years whether we'd expect to experience these extreme wind gusts over points over the open ocean. So as many of you know, that Chaz is a statistical dynamical model used for downscaling of global model data to track an intensity of synthetic TCs. So in our 2021 paper, I tried ultimately to make an estimate of the probability that any given point over the open West Atlantic Ocean or Gulf of Mexico would experience a 70 meter per second wind gust. And so to start with, we took the return period from Chaz downscaled from error interim, looking at the return period of major hurricanes in a 1 by 1 degree box, and find that it's roughly 20 to 50 years for a large portion of the Gulf of Mexico and offshore region of the southeastern US. And this is in the present climate. Through some assumptions made in the paper that's explained in more detail there, we convert this to an expected number over 30 years at a given point location and not at a 1 by 1 degree box, because the hurricane is smaller than a box and most regions in the box won't experience the strong winds. So we have to account for that. And then finally, through some more assumptions described in the paper, we come up with a rough probability calculation of over 30 years, the probability of exceeding 70 meters per second gusts from any hurricane over these points. We estimated a 30 to 60% probability over much of this region, which is substantial if we're building structures that are only designed to withstand such winds. More recently, Juin asked me, why don't you take a look at the CMIP6 models and how Chaz does, and see if we can make an estimate of how this probability might change in the future. So I've been doing that. And so what this shows on the is the change in track density of major hurricanes from the historical period to the late 21st century. For Chaz, downscaled from it's the mean of 7 of the CMIP6 models. On the left is using relative humidity for the genesis component of Chaz, and on the right is using saturation deficit. And it has been mentioned in several other talks, whether future risk increases or decreases is critically dependent on this choice of humidity variable for predicting genesis in Chaz, and it's unknown which is more correct. And we can see that using column relative humidity on the left, you have a substantial increase in major hurricane track density over much of the region, whereas using a saturation deficit, you have a decrease over much of this region. And so we can apply the future track density changes to to Chas error interim and then calculate the implied feature return periods. And so on the left is the return period from Chas error interim historical. And in the center is the estimate for the future return period using column relative humidity to the Sigma 6 models. On the right is saturation deficit. And so consistent with the previous plot with column relative humidity, the return period decreases in most locations, particularly along the US East Coast. But with saturation deficit, the return period increases in most locations. So risk decreasing, particularly in the Gulf of Mexico. And then finally, we can then convert that to probability of these extreme wind gusts and using similar assumptions to in our 2021 paper and see that the probability increases substantially along the US East Coast using column relative humidity, which is in the center plot here compared to the left plot. Whereas on the right plot, which is saturation deficit, you get a decrease in most locations, especially in the Gulf of Mexico. So I want to then now return back to the world of the LES and talk a little bit about how we hope to be able to improve some of the assumptions that we're making for getting a more realistic estimate of these extreme wind gusts and understanding where they are and how frequent they are. So this is the,
Can I ask a
yeah.
question about this?
Yes.
Can you throw the microphone?
Before you move on? Thank you. Sorry, I just wanted to ask about you know the typical structure of these wind gust towers, the red patches you see here, and how do they compare with these delta X?
Can you say that again? Do I know the what?
The typical size.
Size of
Talking about
these
the typical
features?
size of the red patches.
Yeah. So you can see that in this figure, which shows this is a 1 by 1 kilometer box here. So this vorticity structure is a few hundred meters. The wind maxima is like 400 or 500 meters in size. I think that's fairly representative of what these features are in the simulation. So returning to this simulation, what you'll see is that aside from all these small scale asymmetries, the storm is very symmetric. There's no preference for the winds to be stronger on one side or the other. And that's because there's no environmental flow in this simulation. The storm is the only thing there. But we know in reality, environmental flow systematically modulates the structure of hurricanes in a number of important ways, including where the strongest winds are found. It turns out for these extreme wind gusts, we can see from dropsonde observations that the size of this asymmetry. So this shows from dropsonde observations over many storms, all the 70 meter per second wind gusts that have been sampled, relative to shear, where down shear direction is upwards here. And then on the right is a histogram of the distribution of those by azimuth. And so the most extreme wind gusts mostly occur in the left of shear semicircle. And so, stay. So simulations without environmental flow are unable to account for this. And so the overall risk of these wind gusts may be overestimated as a result. If I can get through this. So before I show, so I'm trying to incorporate wind shear and environmental flow and motion of the storm into the simulation through a new capability that George Bryant has added to the model. And so as a precursor to the next simulation, I have a 2 kilometer mesoscale simulation in an environment of moderate shear. So this shows 8 days of the maximum wind speed on the left. And you can see that after about 4 days, you have a period of rapid intensification, and we reach a category 4 intensity. The figures on the right show snapshots at the end of the simulation of 10 meter wind speed at the top and simulated reflectivity on the bottom. What you can see is that even at these kilometer scale simulations, like Falco is doing for its global model, while you can simulate in mean intensity relatively well, you don't get the wind speed and precipitation fields are very smooth, and you don't get these eye-wall vortices or gust result at all. So we need LES in order to study these features. But if we restart this simulation at 250 meters, we can all of a sudden get and run it for about 3 or 4 hours. We get a big jump in the wind gusts. We get 90 to 110 meter per second winds. Again, note this isn't representative of mean storm intensity, but small scale gusts. And on the right, you see that we get, we're able to start to resolve these small scale local wind maxima on the eye wall, and we get realistic eye wall reflectivity. And then from that, we can calculate swaths of wind speed on the left and vorticity on the right for the 2 kilometer run on the top and the 250 meter LES on the bottom. And what this shows is the peak wind speed and vorticity experienced at locations beneath the moving TC over the previous 6 hours. And you can see the effect of individual eye wall vortices on the peak winds as seen in the lower left here, this swath. And there's an asymmetry in the distribution of the extreme wind gusts with a preference for left of shear. And that corresponds with what we think we have observed. And so I'm hoping in future work to sample these simulated towers in the LES with shear in order to get more realistic, spatially varying probabilities for a given location to experience extreme wind gusts. And then I'm also trying to investigate how the RMW may the size of the inner core of the RMW systematically modulates these probability. And in the longer term, more ambitiously, I'm hoping to use these analyses to inform the development of some type of parametric model of extreme wind gusts to use in CHAS or other downscaling models. And so the summary of this work, if it shows up, is that we've showed that LES and dropsons indicate that nearly all major hurricanes possess near surface wind gusts in excess of 70 meters per second. And if you have a direct hit by a category 4 or 5 hurricane, you're very likely to result in such an encounter. And using CHAS, we estimated a return period at any given point location of about 30 to 80 years for a major hurricane for much of the offshore US, which equates to a roughly 30 to 60% probability of experiencing such a gust over 30 years. Using CHAS with CBEP6, we see that the effect of climate change could be to either increase or decrease the risk of extreme wind gusts, and it depends critically on the choice of the moisture variable used in CHAS, and this remains a great source of uncertainty. And then finally, incorporating environmental flow into the LES allows for a more realistic depiction of the shear-induced spatial asymmetry for where extreme wind gusts are found. And that's all I have on that. I don't know if I have any more time to show a couple slides on some other work, or I can stop there if necessary too.
Let's stop here.
Okay, sounds good. Thank you.
All right, well, I think Dan made a good point for running climate models at 30 meters. Questions? Yes. Do we have good insurance? I know, in case anyone gets hurt.
I don't know. That's Giants insurance.
Thank you for your talk. Can you help me to understand how you get the Gusts from a CHAS model? Because CHAS model is statistical model based on training the, I think, 1 minute wind from the fast track. So how do you convert that into the Gust winds that you're talking about? Because later you said you're going to develop a Gust model to incorporate it.
Yeah.
At this point, how do you connect the Gust?
At this point, I am not doing anything sophisticated at all, and I'm really making very simple, crude assumptions that based on the plot where I showed, I'll just go to the. So based on what we see both in the simulation, how the category 3 storm and the category 5 storm, everywhere stronger than category 3 is able to experience these 70 meter per second wind gusts at nearly every location. And then the plot on the right showing that we get this very rapid increase in experiencing these wind gusts as we go from 100 to 140 knots. I am making the assumption that no storms have these gusts that are not major hurricanes, and that all major hurricanes have these gusts. And so that's why I'm just looking at the major hurricane return period in CHAS, and then and then I'm calculating assuming a Poisson distribution for finding the probability of at least one major hurricane passing over a point in 30 years. And so I'm not actually making an assumption about what the gusts are in each storm. I'm just translating return periods to probabilities of major hurricanes. So that's a shortcoming. In the long term, like I want to do something more sophisticated, actually like for any given storm of a given intensity, saying what is the peak gust we expect in this storm. So I'm not doing that yet.
Okay. There there's some engineering approximation or empirical expression to link the mean wing to the gust. You check on those kind of empirical function to say, how far they are from the real LDS.
I haven't looked in detail at that comparison, but I've looked at in the paper, I computed the peak winds in the simulation at 1 minute average to the peak 3-second wind. And it's, I think, a factor of 1.3, which is similar to some assumed distribution, but I think it's stronger than some other assumptions, but I'd have to look more carefully at that.
Liz has a question.
Thank you, really fascinating. I'm curious, feel like your estimates of the risk overland maybe are overestimates because all of your assumptions are of an LES that's not taking land surface friction
Sure.
into.
I'm not making it, just to clarify, I'm not doing it over land yet. That was all meant to be over the open ocean.
But that's what you're showing.
Oh, here, this
For
is
the
just quality.
for the cement stuff, right, with the charts.
The maps.
The maps.
Oh, I mean,
And you're using the assumptions out of your LES model to build those assumptions, right?
well, I'm not meant.
Very high.
Yeah, so I'm not, I wouldn't be interpreting anything over land as being necessarily realistic. I'm only, it's shaded over land, that's true, but I'm not actually meaning to draw attention to that. I'm for now, it's valid, it's only the open ocean.
I just imagine people looking at this without you explaining.
Sure. Yeah, that's why, in the paper, it's done more carefully, but
So
yeah.
it'd be really cool if you could figure out how to get a coastline moving, your LES moving over, coastline moving across your LES simulation, so we see those really.
Yeah, no,
asymmetries and friction effects. That'd be really.
I mean, yeah, that is exactly what I want to do is have simulations like this at very high resolution, but with shear and moving over land. So hopefully in the next couple of years, I'll be able to do that.
All right, I think we should move on. Ben, you're next, right?
Yes. What do I have to do to take this knot?
Yeah, what do I have? Can I just pull out cables or is that gonna?
Yeah. I think you can pull out cables. I think it depends what the problem is, but with a bit of luck, it was the cable, and then that should be fine. But I don't. There's a strong chance that it's.
So when you say this, we need to be concept of your mind. That's what
We don't have a Mac.
I have a Mac dongle.
Oh, do you?
I do.
Okay, that'd be great.
I think we can just do that and then we have microphone.
Okay.
Thank you for con l'assistenza cliente. Oh, thanks.
MPJ.
Yeah, I would start. with-
Another MPJ atmosphere.
Yeah.
Yeah, very good point. Yeah, she did so much in this paper.
Okay.
And it was very hard to,
People on
yeah, to
Zoom
distill it
confirm,
into a
like
clear
maybe
message
someone with
of what advancement the paper has. So it's having a hard time.
Yeah, so it's like.
I mean, it looks like it's detecting something.
Definitely makes sense there.
But I also like, give suggestions.
Yeah, event modeling compound, and then the many different ways of calculating the.
The only challenge with mirror is that you'll have all the.
And then the but yeah, I didn't know that you were working on this direction. So.
Yeah, I was.
Well.
Source of the certain controls.
Yeah.
And make sure that it's.
Yeah, and you also want to.
Yeah. Yeah, yeah. So it starts with the adaptation pathways of Hazelnut and.
Kind of, you need to work. Great.
No, you're gonna jinx it now, it's just like the screen's gonna disappear or something.
If there's a keep going or there's.
Or the projector's gonna light on fire.
But
And it's
it's more.
fully transparent and like it's a way the computer interacts with
There's
the
no-
sphere, but,
They haven't been able to make it optimal, right? Just think, and this is actually for this actually.
Yeah, there was very.
But it's-
Scorecard and risk values, pluses and minuses. Analysis for.
I did it with. Yes.
But this, when we try.
Yes, yes. And I think I pieced it.
Yeah, why would we go this direction at this time?
So you-
Or that direction at that time?
Yeah, and you can handle multiple.
Yeah.
We can.
I've had a AMS where.
It would be optimizing the CBA. It would be ultimately.
All my images were slipped.
Oh, yeah, with the one focus of multiverse, the delay investing.
And I found that out like.
See how, where's the. Yeah, where's the efficient model for many instances in the future. And seeing when the information
You have
comes
it
as well.
on the slide, there's a Tropicana.
So that's one of the key points, when the information becomes available. And see that you,
It was a while back.
so you keep it open. The decision space for when the information becomes available, and then you keep, you reiterate the modeling.
Right.
And that's the merit of your.
Yeah, so you keep the option open and you make decision based on observation, but also make a decision based on your planning that in the future. You're going to
Yeah,
observe.
it's just on the schedule. for
Yes,
each-
yes, take it.
presumably.
So that makes the accuracy much more. But that's actually how we make decisions.
But we just need someone to
When you make
walk
decision
outside and
on
confirm
that.
that they can
Oh,
hear us.
I don't
I can do that, I thought. The only problem is.
Yes, now. Because
Yeah.
when you want to do something right there.
Yeah, because you know that, yeah.
Yeah.
The only challenge is behind the floating meeting control is that someone should be monitoring the chats in the room to make sure things are not too tragic. But I think we can ask one of the chairs, yeah.
Yeah, like, I feel like that's the chair's job.
Yeah, but you have to consider, yeah.
Okay, I'll go
The
outside.
measures are amenable to later adjusting some other measures. There's blockings, right?
Yeah, that's good.
You have to handle them differently. So different
Oh,
sequences
but
of
maybe it
measures.
doesn't rain on your phone, but if you.
You have to treat
Oh,
more
it's maybe
differently
an
with
older
this in
schedule.
your own.
Why don't you ask
For example, yeah.
Stella or?
So
Yeah,
if
just
you,
if you want.
create a
Because I have it on-
reservoir that's creates the, district of a city. Either keep on
But like.
protecting it more and more, or you have to sort of,
Okay, I'm gonna go outside.
Well,
whereas, I don't know, wetlands
On the
or
schedule, it's easy.
other things, they're not gonna go, so you handle them separately, for something that you need.
So we can like that. You can move it forward and make right which floor, you can add weight house and retrofit buildings.
Yeah.
And you can build a bike.
Yeah.
And then you can
Hello,
find the
can you hear me
optimal
okay?
way together.
Yeah.
Like.
Do you wanna try
find
speaking as
out
well?
the optimal-
It's good. I can hear Nate very clearly.
Do you wanna maybe try
So
speaking
like
as well?
when do you
No?
I heard you.
When you renovate house, when you
Oh,
renovate.
yeah, that's true.
So those are the strategies you can find global optimal for all of them.
Yeah, because we manage the components is problem, right?
Yeah.
So once you do the migration from that area,
But I guess.
Yeah.
and the elevation also you can just do it.
By the way, I don't think I've formulated.
Whereas, oh yeah.
Okay.
But the title matters.
From deeper.
When do you?
Yeah,
I'm Tom Duke.
Yeah, I know.
That matters.
Okay,
I work with
Average
James
of
Rupert.
funds also.
okay, yeah, okay,
To do it well.
Yeah.
Yeah, yeah,
So
we
the
work on that.
history of moving the boundary.
Oh, yeah, we
Yeah,
are currently.
and you put constraints
Oh,
and make
okay,
sense.
cool. Yeah, okay, so you already know.
How is the uptake?
Yes,
of
they
this
do.
with,
Yeah, he gave a very nice summary.
Local,
Cool.
local
Okay. Well,
stakeholders.
it was this.
I don't
No, we figure that out. Because I guess it gets very, yeah, very.
But-
Like, it's just like,
But,
skip it on free time.
yes,
Okay.
essentially, if you think about it.
I couldn't tell.
So the OU one was the first.
Yeah, yeah.
And I think it was easier once.
Yeah,
it's-
well, as long as they see that they can,
Yeah, easier, but like,
constraints
OU
in terms of their
was the
preferences.
ones that were
Yeah.
given
And,
advantage to students, so it's
Yeah,
cool that you
politically.
guys- Was it
Decisions about the history, because that, and then you can incorporate that, and then you.
That's a great, like.
Yeah.
Black box plots.
Yes.
Yeah.
Maybe they can.
I mean, the thing
Yeah.
is, the only thing is,
Yes.
I believe,
Yeah, all that, yeah.
I guess
We're lucky to have.
they are already talking about flexible.
Oh, you also have faculty?
No, I'm a research.
Okay, okay.
How
I
do
work at the
you
National
establish
Yeah.
Yeah, yeah.
Like, what is it?
We need to adjust over time. It takes some effort.
Yeah, just got it.
I mean, just to.
Because
Yeah.
the-
They do everything. Everything in the finance, Genesis.
Yeah, yeah,
So they cannot-
yeah, probably there's someone in the office that does things the right way and they want
Yeah,
to do that.
that's a challenge.
For now.
But everyone's talking about flexible.
So it made sense to have the break.
I did, that was a really good, yeah.
Yeah.
And we're just gonna use one,
Good for
we're gonna use Tom's
Yeah.
computer.
Okay,
My
okay.
pocket.
Nice.
Simplify.
Thank you for your feedback. Sorry.
No, no, thank you.
I want to test it with and without them.
Not everyone can go out.
The best, yeah.
Mind the game, please. Please mind the game. Mind the game.
Is that true?
Mind the game. Merci, donc. Je voulais
C'est pas 5 mois qui j'en ai fait maintenant.
Ouais, j'ai vu ça.
Ah ouais, mais
C'est pour ça que je dirais-
Non, mais c'est le monde que je peux faire quand on peut pas.
Ok.
I mean, I'm not using that.
So his method.
Was every, do we need the mic for the room or was that okay?
It works.
It works? I mean, just for the room.
Oh, for the,
Yeah,
oh.
for,
So for the room, we need the standard mic.
I mean,
Well, unless you can
Dan,
hear
I
me.
think Dan was loud enough, so are you as loud as Dan?
I think I'm pretty loud. Or you said not,
It's just a normal mic if you want to try it. But I don't know if it's plugged in. Does this work at all? It does? Okay. Do you like mics?
Yeah, I'm okay without it. Yeah.
Okay.
If it becomes a problem, let me know. I'll just hold the mic and.
We need at least one person monitoring the Zoom chat because we
I can do it.
panel so that if we have people chat like sending messages that they can hear anything. It's like if one person could look at this chat.
I can do it.
Okay, awesome, thank you.
All right, let's start again. Next up is Ben Schenkel from OU or NSSL 0. Somewhere in Oklahoma. You're from.
Oh, I know zero.
And now we'll switch gears, TC intensity, extreme wind gusts. Now we're going to TC size, and Ben will talk about how will TC outer size change by the late 21st century. All right, Ben, it's all yours.
Yeah, thank you, Falco, and thank you for the opportunity to speak today. I'm excited to talk about some of the, I do a lot of work with outer size, and this is kind of one of my final projects, I think, on outer size before I transition on to some new work. So I'm excited to talk about it. So this is work I've done in collaboration with Ning Lin, Dan Shabazz, Gabe Becky, Tom Knudsen, and Hans Bremer, and support from the NSF. So yeah, I'm a research scientist at the National Severe Storms Lab. And let's just get right into answering this question. I hope you'll be able to answer it or know what the answer is by the end. So to begin, what I want to start off with is a schematic that this is kind of from a dated paper, but in terms of like how TC characteristics will change in a future climate, I feel like this figure sums up our current understanding or what we actually like to focus in on. So what this figure is showing is the percentage change in TC and a couple of parameters here. The blue bar indicates the expert judgment, and then the 67% confidence interval is the blue shading about that. So as an example for TC frequency, what we see is that there's an expected decrease potentially, but there's a lot of uncertainty about that. Similarly, category 4 to 5 TC frequency, there's an expected increase, but still some uncertainty. Lifetime maximum intensity and precipitation rate, there's some inclination that it's going to increase in the future climate, but maybe there's some uncertainty with that. I think one thing, though, that's not summarized in this plot, and one variable, but that's not summarized in this plot, but is worthy of looking at, is TC outer size. And so by the end of this talk, I want to ask if we can add a fifth category to this figure showing TC outer size, given its importance to estimating things like storm surge or tornadoes. Tornadoes is something I focus in on a lot, so in landfalling hurricanes. So if that's something you want to talk about after this, please let me know. So let's get into what I mean by TC outer size, because I don't think it's something we talk a lot about. So how do we define outer size? So what I have here is an example of a satellite image of Hurricane Irma when it was off the coast of Cuba. The infrared satellite image is showing all the convection with the deeper reds indicating colder, more intense convection. And then overlaid on this are some characteristic size radii. So at the center, we have our radius of maximum winds. That's from the IBTRAX data set. Outwards of that, I have R64 knots or hurricane force winds. And if you keep going out, you get to R34 knot winds, tropical storm force winds. Way outside of that, I have this R12 metric. That's our radius of 12 meter per second wind that has been used in prior work by myself and others. And what this is basically is it's an azimuthal mean metric where we've looked for the first grid point outside the eye wall where the azimuthal mean tangential wind speed at 10 meters equals 12 meters per second. Similarly, radius of 8 meters per second is similarly defined, but just looking for the 8 meter per second threshold. So how does this relate to size? Well, not all these are outer size metrics, but when we look at outer size, we see that typically outer size, and let me try to move this so it's not in the way. Outer size is typically used it's typically looked at in an azimuthal mean sense because the TC circulation is pretty symmetric. And it's calculated from 10 meter winds. This is really important for hazards estimation. We define TC outer size typically at radii where the wind speeds are weak and convection is more sparse. So if I had to subjectively estimate which one of these are outer size metrics, I might start at R34 knot winds, so the radius of tropical storm force winds, and really I think R8 actually does the best job of defining regions where the convection is sparse. You really at that radii, that outermost circle, you have a lot of serious but not really deep convection necessarily going here. I will note there's a large variety of metrics used to define TC outer size. It's not like intensity where we have 10 meter winds and minimum sea level pressure. There's really a lot of this lack of one metric is due to our limited observations that we have, but we do the best we can, and they're largely pretty well correlated with each other in spite of that. So with an idea of what maybe outer size is, I want to next talk about how does outer size vary over the lifetime of the storm. Oh, and one last thing. In this study, we're going to use this R8 metric that I've circled here in black. We use this because it's well represented in reanalyses. And reanalyses are kind of a sanity check for some of the simulations I'll be showing later in this study. And it's also for consistency with prior work that I've done as well. So I next want to get into a schematic to show you how outer size typically, or outer winds typically evolve over the lifetime of the storm. So what I have here is the black line shows streamlines here, and the shading is my attempt at showing ice attacks. And in this situation, I'm just simply considering two easterly waves in the Atlantic of different sizes here. So we have the one on the westernmost is smaller than the one on the easternmost. And I'm going to ideally just simply consider that they both form into TC. So if you have these easterly waves of different sizes, we might expect that the smaller wave leads to a smaller TC, and there's been work showing this, and vice versa as well. So that TC outer size at genesis is set by the outer size of the precursor disturbance. So that's fact one to know. Why this is important is we see that large TCs typically grow faster than small TCs. So it's really important to be able to estimate what the outer size is at genesis, because that has implications for later on. In essence, the TC has a memory of its initial size. If we look like a day later, we'll note that this smaller TC has, I've tried to show it has a stronger intensity, while the larger TC has grown but has a weaker intensity. So one of the things we see is that large TCs are less likely to rapidly intensify than small storms. So I think that's something that size has some relationship with intensity as well. TC outer size does vary more slowly than intensity, such that the two are weakly correlated. So there's this relationship between size and rapid intensification, but there's not necessarily a relationship between outer size and intensity itself. So if we keep going further in time, I've tried to show this is getting closer to the lysis of this westernmost storm. And I've tried to show it contracts a little if I toggle back and forth, while the larger storm continues to expand in size. So what I found in some of my work is North Atlantic TCs grow throughout most of their lifetime and then kind of decrease at the end of their lifetime, or as they're undergoing extratropical transition. We also found in some of my work that TCs that traverse the greatest distances, those that recurve into the mid-latitudes, tend to grow the most in outer size here. So lastly, that we're now considering the same easternmost storm that's recurved into the mid-latitudes. I'm assuming it's undergoing extratropical transition. And what I found is that TCs that undergo extratropical transition become asymmetric, and that's a lot of other studies have found this as well. But they tend not to expand until after transition ends. So that's kind of the new wrinkle on things. And that's some work I'm doing with an undergrad that we're looking to submit for publication in the next month or so. So the last thing, or one of the last things I want to talk about, is that there's large variability in this genesis outer size and subsequent outer size growth rates. So as Ning talked about yesterday, you get this long log normal distribution with a long right tail for your R8 distribution, or any metric you choose to use. I think one thing that we're really missing, though, in the outer size community is we lack a complete understanding of which factors are most important in impacting the life cycle of outer size. So there's been like a veritable laundry list of things that have been correlated with outer size. We have no idea as to the relative importance, and I think we're still kind of trying to figure out what that is. I'd say the most promising work, though, is being done by Dan Chavas at Purdue, where he's looking at the relationship between outer size and the Rhine scaling and relative SST. So I think his work is kind of on the right track to sorting this all out. So then with this kind of understanding of how TC outer winds typically evolve, the next question is, what about in the future climate? Because this is, after all, what I'm after. So the answer to this is there's not a ton of studies that have looked at how outer size evolves in a future climate. So this is actually one of the few studies. This is from Knudsen et al. 2015. What it's showing is the distribution of outer size in the black line is quickscat for the observed period. The blue line is for the model. The red line is for the late 21st century under a warmer climate. And what metric is being shown here, again, this is a different metric, is the radius of 12 meter per second winds. So we're looking at where the azimuthal winds first equal 12 meters per second outside the eye wall. And what's being shown by the X's here are the median values of the distribution. and the sample sizes are on the right-hand side of the figure here. So these simulations are just for North Atlantic TCs, and they're from a high-resolution GFDL hurricane model simulation of the current climate and late 21st century conditions using RCP 4.5 conditions here. So what this study has shown is that North Atlantic outer size tends to significantly shift towards larger values by the late 21st century. And that's actually in agreement with some studies, including by Alyssa Stansfield. She's looked at this as well. But then there's been a lot of other studies that have suggested there's no significant changes in outer size by the late 21st century in the North Atlantic. So there's this really lack of consensus. And I think one of the downfalls of some of these studies or maybe criticisms you could make is they're using like a single model with a single greenhouse gas emissions pathway. So it's kind of, we don't really know how to compare some of these these studies amongst each other. So I think where we fit in is we're going to use a variety of models and greenhouse gas emission scenarios to try to see if we can come up with an answer among all the models that we're using that comes to like a consensus here. So I want to bring up some motivating questions for our study, and we'll get into some results, I promise. What can we learn from a multi-model study using multiple greenhouse gas emission scenarios about changes in TC outer size by the late 21st century? Are there changes in outer size and structure that are confined to certain portions of the TC life cycle, i.e. like genesis or the end of life cycle? And then are there changes in outer size and structure that only occur in certain regions of the North Atlantic? As an example, do you see that storms that recurve into the North Atlantic, do they tend to become larger in the future climate? So these are the questions we're going to focus on for this talk. So to get into how we approach this, I'm providing the first multi-model assessment that I'm aware of to look at how TC outer size changes in the late 21st century. We're using 3 models to quantify the response of TC outer size to anthropogenic warming. And as a note, I've excluded the extratropical transition portion of the life cycle of the storm. I think that's kind of a different question to ask, and it's something that people really haven't looked at either. But if someone has the time, I think it's something that should be looked at. So the 3 models I'm using is, one of them is the GFDL high floor model. It's a global coupled model with 25-kilometer grid spacing within a repeating identical cycle of radiative forcing and SST nudging the climatology. The emission scenario here is CMIP 5 RCP 4.5. So for those of you who are not familiar, our emissions decreased and then stabilized by 2100. The second model we're using is the GFDL version of the GFDL hurricane model from 2012. It's a regional coupled model with 6-kilometer grid spacing, so this is much higher resolution. And it's downscaled from a HIRAM global model simulations. This is also RCP 4.5 for the emission scenario. The third model we're using is another version of the GFDL hurricane model. This is an older version with a slightly coarser grid spacing of 9 kilometers. And this is downscaled from a ZTAC regional model whose initial and boundary conditions come from the ENSA NCAR reanalysis. So it has some memory of what current climate, or it has some indication of what current climate variability should look like. Here, the emission scenarios considered are CMIP 5 RCP 4.5 and CMIP 3 A1B run with the CMIP 3 A1B scenario has been run with both a multi-model mean and 10 ensemble members. So we have a lot of simulations to suffice it to say, and a lot of data to work with. And for CMIP 3 A1B, again, this is greenhouse gas emissions decrease but do not stabilize before 2100. So the design of this is they all have a current climate simulation with radiative forcing and SSTs taken from 1980 to 2006 period, put very simply. For the future climate, we've simply taken the anomalies from the CMIP 5 or CMIP 3 models and added those to the control conditions to get our future climate simulations. We also have ERA 5 data that we're using as a sanity check for our models from the current climate. And the metric we're going to be using is the radius at which the azimuthal mean 10-meter azimuthal wind equals 8 meters per second. And we've removed the background flow using the methodology that Ying outlined yesterday in her talk. So what we're going to be doing is examine differences in outer size and structure between the current and future climate, including life cycle variations and the spatial variability in the outer wind size and structure in the North Atlantic here. So let's finally get to some results here. my first set of results, and I just want to show a subset of the simulations to begin. I'm showing the distribution of this R8 metric on the x-axis as box and whiskers plots here. And the metrics, the statistics that I'm really focused on are the 5th and 95th percentiles, which are the diamonds overlaid on the box and whiskers plot, the box perimeter, which is the 25th and 75th percentiles, and then the median value is the center line here. I also have the 95% confidence interval as determined by 1,000 sample bootstrap sampling approach here to give an idea as to what the uncertainty is with the median here. This is for that high floor GCM 25 kilometer grid spacing model for the control and the future climate. So if you eye this, there's like a subtle shift towards larger sizes, but this is actually not in any of these statistics I've shown here, they're not significantly different in any way. There's a shift, but not non-significant. So if I bring up some of the other simulations I have, I'm not showing the CMIP3 A1B because I just think it becomes overload. But what we see among all these simulations is there's no significant changes in outer size by the late 21st century across any of these distribution statistics. That's the common theme here. And this is, I think, consistent with what we've seen the past week or so, right? Liz Ritchie, Colin Zarzicki, Rosemar all showed that as the climate warms, there doesn't tend to be much of a response in the outer wind field of the storm. So this makes us feel at least more confident in this. The other thing is that the sign of these non-significant changes are really inconsistent among the model simulations. So in blue on top, this GFDL downscaled simulation from the ZTEC model suggests maybe a slight decrease, whereas the PyRAM downscaled GFDL hurricane model simulation and the high floor simulation suggest a slight increase. So even the sign is not really consistent in these non-significant increases for what it's worth. So the next thing I want to show is variability in the TC azimuthal mean winds. So I want to show that what I'm showing is not an artifact of the metric we've chosen. I'm not playing any games here, essentially. This is what the azimuthal mean 10-meter wind speed looks like for the TCs in a composite sense. For the control in blue, and the red is CMIP 5 RCP 4.5 for our high floor GCM simulation. The dashed lines indicate the interquartile range of the wind speeds. The solid line is the median, and the 95% confidence interval is the shaded region. So what we see here is there's a lot of overlap. At least in the inner core, there's some indication, as if you look at the 75th percentile especially, that you've shifted upwards in wind speeds, indicating the storms are more intense. But the outer periphery, if we start looking outwards at 200 kilometers, there's really a subtle shift of like a meter per second or so. And it's really not much of a change, to be honest. I can bring up some of the other simulations to look at here. So this is one of the downscale GFDL hurricane model simulations. It's the same story. The lines are pretty on top of each other outside of the inner core of the storm. Here's another one of the GFDL hurricane model simulations. There's even more overlap in this one than some of the other ones I showed. And then here's the first time I'm showing these CMIP 3 A1B simulations where we have 10 ensemble members, and there's also a lot of overlap here as well. So if bringing these all back, I think the main takeaway is that there's no significant changes in TC outer winds in any of these simulations. If we're looking at radii where R8, our outer size metric, is typically defined, that's like roughly 250 to 650 kilometers from the center of the storm. You can see there's a lot of overlap in the distributions, and the differences are not significant. In contrast, there's a shift towards stronger inner core winds in most of the simulations. So I've tried to highlight those models that show that. So again, that outer size and outer size is kind of decoupled from intensity in a lot of ways. So some motivating, I want to bring back these questions and try to answer them systematically. So for that first question, we see that consensus exists among multiple models that projected TC outer size and structure will remain unchanged by the late 21st century. And this assumes a decrease in greenhouse gas emissions later this century. I don't know what things look like under more aggressive emissions scenario. So let's try to answer these last two questions with the remaining time I have. Is everything okay? Okay. Cool. So first I want to talk about the lifetime variability in TC outer size as the kind of the second question to answer. So one of the challenges with this is we know TCs have a lot of variability in how long they live. So to get around that issue, what I did is I constructed a normalized life cycle coordinate. So 0 in this coordinate would be genesis, and then 1 would be either lysis or the beginning of ET, because I'm not considering extratropical transition. And so I've taken the outer size and interpolated it to each of these like normalized bins, where I guess 0.5 would be a middle-aged cyclone. And here are the sample sizes for each of the data sets I'm working with. Again, for this high floor GCM model, I have R8 here on the y-axis. So you can see that over time, as I discussed in the introductory material, we see this gradual increase in size, both in terms of the median, which is the solid line, and then 75th and 25th percentiles here. I have the ERA5 as a reference frame here. So there's actually quite good agreement between the control and ERA5 simulation. But you don't see much of a difference between the control and CMIP5 RCP 4.5 simulation for this high floor simulation. Again, suggesting that these differences or these lack of differences are consistent among the entire TC life cycle. So let's show the other models just for showing these for the sake of it. I will note there is an inconsistency between the ERA5 outer size metric and this is one of the GFDL downscaled simulations. That's because we use the lowermost model winds, which are not located at 10 meters, they're located above that. So that's why we have these slightly larger storms, but we don't believe this affects or results in. Similarly, here's one of the ZTAC downscaled GFDL hurricane model simulations, and this is the CMIP 3A1B ensemble kind of all shown together in a composite sense. So putting these all together, it's like I sound like a broken record, no significant changes in outer size at any point in the TC life cycle across our simulations. We do see small non-significant changes in TC outer size depending on the simulation, and these like kind of towards the end of the life cycle, but again, these are not really large differences by the end of the life cycle of the storm. So the last thing I want to focus in on is kind of the spatial variability in TC outer size changes. So what I did is I took all our simulations for, in this case, our high floor GCM. I took all the TCs from the control simulation. I divided the Atlantic into boxes, and I just took the median outer size within the grid box for the control, for each grid box for the control simulation. I repeated the same thing for our RCP 4.5 simulation, and then I did the RCP 4.5 minus the control. So what this gives you is how much things have changed across the Atlantic. The warmer colors indicate that we've had size increases. The cooler colors indicate decreases by the late 21st century. The panel on the right shows the zonal mean in case you're interested. But what we see, at least for this high floor simulation, are kind of subtle increases, but they're kind of on the order of about 10% of the size metric itself. And none of these grid points are significantly different. Surprise, I guess. What we see is a ton of variability in outer size differences at each grid point, such that none of them are different from each other. So that's kind of the big takeaway from this. If we look at some of the other models, we see some agreement. This is from the high-RAM downscaled GFDL model, and this suggests maybe even more aggressive changes in size. But again, these are not different either. Here's that ZTAC downscaled GFDL hurricane model. Now this is suggesting a decrease in size. So again, this inconsistency in size between simulations here. And then here's the A1B ensemble simulations all aggregated together. And this also suggests a decrease. So we have this inconsistency in size changes here. So putting it all together, we see no significant TC outer size changes at any grid points across any of the simulations. There's some agreement in spatial patterns among some of the models, but they're really small differences and they're not significant. I don't know how this would change if we had a more aggressive warming scenario. So that's something to, hopefully we don't have to think about that possibility, but that's something to consider here. So to answer these remaining questions, which are really the key takeaways of the talk, are changes in outer size and structure confined to certain portions of the life cycle of the storm? I would say no, they're not, very simply. And do changes in TC outer size and structure occur only in certain regions of the North Atlantic? I would say no, our simulations project no localized changes in TCR size in the North Atlantic by the late 21st century. And this assumes, again, certain that our greenhouse gas emissions are decreasing by later in this century, and we're not considering how things might change during extratropical transition either. So those are two worthy things to study. So this work I want to mention also agrees with recent theory by Dan Chavas, suggesting that maximum TCR size should not change due to anthropogenic warming. And if you want to read more about that, his papers on the Rhine scaling provide a theoretical framework for sort of understanding these changes. So I think we're getting to the point where we feel somewhat confident that at least outer size won't change. So bringing back this figure from the start, I kind of want to add my take on what outer size might do. So here's what I'm suggesting based on my work and others. I'm not an expert, so maybe I shouldn't have this expert guidance for mine, but this is what I'm thinking. So, but feel free to disagree with me if you have strong opinions. And if you're interested in this paper, here's the reference. This came out in late 2022, but happy to answer any questions you have about it. So in the last minute or two, I just want to bring up some additional questions, kind of channeling some of the thoughts we've had the week and a half of Tropicana, or at least that I've been here. So one of these is, do the lack of changes in TC genesis or genesis TC outer size suggest that the outer size of TC seeds will remain unchanged by the late 21st century, given that relationship between genesis outer size and the outer size of seeds? That's one question. I'm wondering if that provides some insight into things. I don't know. Thinking about some of Liz Ritchie's talk and Wei Li's talk, which is maybe, this is definitely more relevant to Liz's work than Wei's, which is more dependent on intensity. But what do these results imply for future changes in how TCs redistribute heat within the climate? I think that's a worthy question to ask now that we maybe have a better sense as to how TC outer size may or may not, or doesn't change in the future, at least for these greenhouse gas emission scenarios. And then lastly, what are the implications of these results on hazards? We're going to be talking a lot about that, I think, for the rest of the week. What does this mean? A lot of the prior literature on TC hazards projections have assumed a static outer size. And I guess we've lucked out, and at least that seems like not a bad assumption. So yeah, what are the implications? So with that, I'll take any questions you may have.
All right, thank you, Ben. Time for a few questions. Let's start with early career first. Oh, sorry.
Hi, Ben. Thank you for your interesting talk. I was wondering, I may be wrong, but you said at the beginning of the talk that we calculate the outer size based on temperature and speed. So you show in the previous graph that in the inner core, the 10-meter wind speed is going to increase, like much more than the wind speed in the outer size. That means that the ratio between the inner size and the outer size will change in the future. And if so, which is your physical interpretation of that?
Yeah, I think so. That's a good question. We tried looking at inner size actually, but I don't think the models are great for that. I think still, especially the high floor model is, I think it's too coarse to resolve a reasonable RMW, to be honest, at 25-kilometer grid spacing. For some of these GFDL hurricane model simulations, maybe you can start to suggest they're starting to resolve the RMW and the variability that you have, but I don't really see a ton of contraction, at least from a composite perspective, in the radius of maximum winds. If anything, it's just kind of pushing up to stronger wind speeds. What does that mean for, I think maybe we have to be more focused on like what's going on, how the inner core is changing more than the outer size. And that's really where the strongest winds and a lot of the worst hazards are going to be concentrated anyways. But I think the RMW question is still something that's out for debate. And Liz gave a talk where she talked about that, I believe, and Colin to some extent. So I think that's a question that's up for debate, to be honest.
Thank you very much.
Okay, sure.
Thank you for a nice talk, and I have two questions. The first one is, have you ever looked at the change in the track or attributed to the change in the size? And the second question is the unchange of the outer size conclusion or apply to other basin, like Western Pacific.
Okay, the track, I'm sighing because I think these are good questions that I don't necessarily know the answer to. So the first question, I think we do know the answer, and that's, yes, there are track changes. Is that kind of muddling our results a bit? Maybe, but at least if you consider at a given grid point, you know, at least we're trying to do as apples to apples as we can, accounting for those track changes. So yes, I think that does kind of put a fly in the ointment of the results. The track changes are not something we can kind of separate out from this, but I think we at least try to account as best we can with this. For the second question, it's a really good question. I don't know. I think a lot of the literature has been focused, or at least some of the simulations have been more focused on the North Atlantic. And then the simulations that I know of that have dealt with other basins actually show a mixed signal. Like, so Western North Pacific TCs actually are supposed to grow in size. But then if you look at like the Southern Hemisphere, I think they're supposed to shrink in size. And to me, that's not clear as to why that should be. That almost to me suggests that whatever impact anthropogenic warming has, it's maybe there's some non-linearities that are, or more important, like track changes that maybe are influencing some of the signal area. But it'd be worthy to extend these results to other basins. I think that's the logical next step.
Maybe one more quick question. How much the back?
Yeah, thanks for the nice clear talk. I really like the figures, the pamphlets. I was wondering, have you looked at the differences in model systems between your simulations and in particular the wind drag schemes? Would that explain the differences potentially in the results for each?
Yeah, I mean, we haven't looked at that. I mean, that's a good thing to look at, or would be a good thing to look at. Obviously, that's going to impact our results a lot. The fact that we don't see differences, I'm sure there are pretty substantial differences in that among the models. The fact that in spite of that, we don't see a lot of strong differences, I think suggests that maybe that's not a strong factor at the end of the day, but it's something that I wouldn't rule out, and it's something we should definitely look at. Is that our results a red herring for like some of the differences among the models in that? Yeah. So.
All right, okay. I think we can switch now. All right, next speaker, last speaker before lunch break is Tom Beucler from the University of Lausanne. And I think he'll be talking about machine learning. I guess we're switching now to the machine learning portion of this meeting. Hopefully the transition is.
I just need to download.
All right. So, is there any other question? Maybe for quick question for Ben.
Yes, perhaps the way to go is like to use like, because you mentioned that there are all these I don't know if it is, but there are all these mentioned with basins and different results. So what about using a idealized model or aquaplanet model that we were seeing yesterday? Like if we do this experiment in an aquaplanet with warmer sea.
Yeah, I mean, I think Alyssa, you've done.
Yeah, I've done some aquaplanet simulations. They're a bit simpler than what Rosie did though, because mine are fixed SST with the whole planet, so it's like a kind of RC type simulation. And yeah, I did some work looking at the sizes, which the sizes do increase the simulations.
Yeah,
like
everywhere.
Well, that's the thing. So they don't really change in like the tropics. The changes are like near the poles because they can exist near the poles. So that is kind of gives credit to, I think, Dan Schwass's idea that like in the tropics, the sizes are kind of set by the dynamics of the planet and not so much by the dynamics.
Yeah, so I think he was really excited by your work and trying to validate this Ryan scaling parameter to agree with his expectations. It's very much.
Thanks.
All right, thank you. All right, now Tom and company.
Fantastic. We'll be experimenting and giving a group talk first. I want to thank you all. I've learned so much. I've been challenged in a really stimulating way. I want to thank, I think Susanna is the one who sent me the invitation. So I really want to thank Susanna because I wouldn't be here without her, and her group has been very welcoming. And so we will be talking about some the results we've found over the past 2 years as we've delved into the topic of a very general topic of how AI can help tropical meteorology. But before that, I want to give a quick primer on what my research group does at the University of Lausanne. So we explore the nexus of atmospheric physics and machine learning. And I think of machine learning in the broadest sense. So any model that can learn from data without being explicitly programmed for a given task. And I like to think of it as a two-way interaction between our knowledge of atmospheric science and data-driven modeling. So on the one hand, you can use knowledge to guide and restrict the output of data-driven models to solutions that are plausible. I'll give a quick introduction to that in the afternoon. And on the other hand, what's really exciting from a scientific standpoint is that you can systematically discover new equations, new patterns, new creative ways of analyzing the output of storm resolving simulations that can't be always analyzed using traditional methods. And so this is a really exciting topic. Our application topics are mostly threefold. We're really interested in weather application, in particular extreme weather events. We work on forecasting, post-processing, but also process understanding, as Frederick will show you. I work a lot, and now we have funding to work more on climate and Earth system modeling. We've worked a lot on not only just accelerating, but also improving parametrizations, because they really remain at the heart of the uncertainty we have when we make long-term climate projections using models. And finally, we also work on climate impacts, downscaling, and risk. But today we'll mostly be focusing on the weather part, and we'll be focusing on tropical meteorology. And before we get into forecasting, I think Frederick is going to tell us about process understanding. So thanks.
Hi, thank you. So yeah, I'm going to talk about a little bit about how to use like machine learning to analyze like a storm resolving model. Like the goal of this is to discover patterns like within those simulations that is correlated to the genesis of the site. So this work is an ongoing collaboration with James at OU. So the idea of trying to discover scientific knowledge has a lot to do with discovering patterns. So I'm showing an example of a supercell cases, trying to understand which kind of supercells would have a lot of parallel particles forming. So what we can do, people are doing is like overlaying like a different sort of contours and shading representing different physical variables, and based on that, like we can have some knowledge about the process that leads to hailstorms. So but the problem is, how do we objectively discover those patterns? So I think what we are proposing here in this research is that we can use machine learning for this purpose. So the scientific question that we are targeting stems from like a lot of simulation that we are kind of surprised about. So I'm showing two warp simulations, one both on Hurricane Maria. So in the simulation on the left-hand side, like we have a simulation where we always turning on the cloud feedback, like the feedback between the radiation and the clouds. And when we turning off this cloud feedback at certain times, like we are seeing this real simulation that the storm completely fails to intensify when we're looking at the shading, which is the surface winds. So what we can see is that there is a first order effect between the cloud feedback and the intensification of tropical cyclones. So what in the previous paper of James Beucler, they've shown a sort of similar schematic diagram of this. So what they are seeing in this diagram is that if we have this cloud feedback, specifically the coverage of long wave radiation by clouds. So what it does is it creating a secondary circulation, which can drive a lot of moisture and momentum into the inner core, which can allow the storm to intensify and generate. However, what you might notice is that it's primarily a two-dimensional diagram. The reason behind this is rely on a lot of diagnostic framework, which rely on certain assumptions. So we can only have this understanding in two-dimensional. So what it doesn't allow us is to understand certain type of problem, like for example, will asymmetric cloud reinforcing bring additional or less interpretation compared to the two-dimensional counterpart. So what we try to do, try to understand this scientific problem is to try to, can we use machine learning to do this? So what we have done in the past 2 years is that we are trying to analyze those simulations that Jane provided and use machine learning model to try to process it a little bit and try to understand things. So the idea is that in the water simulation, it will have a lot of radiative structure anomaly associated with, for example, deep convection. You have a structure related to shallow convection, for example. But how does it relate to the interpretation of tropical cyclone? So what we do is we define a machine learning model that predicts the interpretation rate in 24 hours. And we try to say, okay, how much of this deep convection radiation contributes to the interpretation and how much the shallow convection contributes. And so we combine all this together, we'll be able to find a characteristic pattern, like an optimal pattern that correlates the most to the interpretation rate in the next 24 hours. So by understanding this pattern, we may be able to understand some new scientific knowledge about the physics behind TC genesis. So when we look at this structure collapsed into a 2D diagram, first of all, we can see that if the model finds a pattern that is closest to this extracted pattern, it will predict a high interpretation rate. So when we understand this pattern, analyze the pattern, we are seeing that it corresponds to an area here with a more deep convective signature in the inner core, which is not surprising. But also we are seeing another structure which is quite surprising to us is that there is a sort of a boundary between inner core and outer core. There's shallow signature, cloud top signature that is the cloud top is around somewhere around 900 hectopascal. So we are seeing two distinct signature that is correlated to the interpretation of tropical cyclone, at least in our case. So one thing that's pretty interesting to us apart from this is because we have identified three-dimensional structure, and with this we are able to understand some of the problem that we proposed earlier, understanding whether or not asymmetric radiative structure makes sense, relates to the interpretation or not. So what we found is that basically both of those structures, no matter in the lower levels or the upper level, both have a distinct wave number one anomaly. So we can also see that the upper level signature is distributed downwind of the shallow cloud signature, suggesting a potentially causal relationship between the two of them, which we will be able to test in the next in subsequent research by using water simulations. And with that, I'll move to another part of the presentation, which is using causal discovery for short-term tropical cyclone forecasting.
Okay, great. Thank you, Frederick. So I hope Frederick convinced you that you can use simple machine learning model to not necessarily fully answer, but at least generate scientific hypotheses that can then be further investigating. Now we're going to switch gears and talk about forecasting. And this is work that was led in almost all of the credit goes to Sharanya Ganesh Sudish. She was a postdoctoral researcher in our group for 2 years, so most of the results I'm showing are hers, even though we are a very collaborative lab, so we all had to we all helped a little bit as much as we could. And what she got really interested in is whether causal inference and causal discovery methods could improve statistical forecasting in a general sense. I'm going to talk about tropical cyclone today, but you can think of it for any kind of weather system. And to motivate the topic of causal discovery, I want to start with I want to start with a very, very local example. So it's 11:40 a.m. and right now the sun is heating the Institut Pascal. So you probably noticed the room is getting warmer. But what happens is the sun also, I think surface shortwave heating also increases photosynthetic activity. So plants outside will also generate will have a higher photosynthetic activity because of the sun. Now, if I design, and so what we would say here is that the sun is a confounder of these two relatively independent phenomena. Now, they may correlate very well. So if you have a very naive model, it could learn to predict how hot this building is from photosynthetic activity. And then if we have an interventional system, so typically, I don't know if you saw, but there were boars in the forest, I saw two of them. These boars may eat the plants, and then that photosynthetic activity will go to zero, and then the naive model would just predict that this model cools down. So I hope this motivates the fact that if we have knowledge of the underlying causal graph, we may want to take it into account when we design regression algorithms, in particular for forecasting purposes. And so in the Earth system, we work with multivariate observations. You can consider it as a multivariate time series problem once you've reduced the spatial dimension. So we have all these time series of different variables, and these can be used to discover an underlying graph using different causal discovery methods that use different assumptions. And for example, if you wanted to predict x1 here, and what you can see is that x2 is what we would call a parent of this child variable, while x3 and x4 are correlated, but only spuriously associated with x1. And what you may want to do is just not consider x3 and x4 in your regression problem. So it's a very simple case where all we're saying is, okay, if you're going to predict x1 only keeps its causal parents. We've shown in the case of climate modeling for the design of machine-learning convective parametrization that if we train a neural network in a non-causal configuration, and then compare them with neural network that were informed by the causal discovery methods, the ones that were informed don't learn spurious association, for example, from stratospheric water vapor to convective activity, which we know are spurious because convection is bottom up. So we can get more physically consistent parametrization by taking into account knowledge of the underlying graph. Or at least parts of it, the part that's relevant. Now, in a couple of minutes, I'm going to say how we think this could be helpful for short to medium range tropical cyclone forecasting. So first, I'll give a brief overview of a paper we published which introduces the new causal discovery methodology that's a bit underused, but really helpful for physical phenomena before delving into how we think these methods can use schemes that are operationally used. So we're collaborating with Sierra to see if we can come up with new shifts predictors or remove some of them. So the setup for the first example, when we do methodological development, we like to put ourselves in relatively noise-free cases. So we developed the methodology on Area 5. So for that, we considered northwestern, West Pacific tropical cyclones. We also worked on the Northern Indian Ocean. And what we do is using the best tracks from ID tracks, we extract a lot of variables. So our goal is to generate new hypotheses. So we're trying to come up with predictors that people didn't necessarily use. So we take a ton of variables and then we area average them from 0 to 200 kilometers mostly to describe the inner variable. I'm putting inner in quotes here because you get some of the inner ring bend sometimes if you average up to 200 kilometers. But most importantly is to distinguish variables that are more linked to the tropical cyclone itself and to the surrounding environment. So we'll just call them inner and outer. And then we try to find which of these variables should be added or removed for the prediction of intensity. And so what we do is we convert schemes where we throw all the variables in to schemes where you feed the variables of the training set to a causal discovery algorithm, and then we only keep the features that the causal discovery algorithm tells us to keep. So we only keep the causal parents. The problem is if you do that using traditional causal discovery methods, every single tropical cyclone will give you a separate graph. But now, usually, I'm a physicist, so I like to think that tropical cyclones are several realizations of the same underlying phenomenon. If you think that, then you can make the assumption mathematically that they obey the same causal graph. Once you do that, you can sample the same causal graph much more efficiently, and you can, and so you have more statistical robustness. Plus, you only get one causal one set of causal parents at the end. And so this is what we call multi-data causal discovery as opposed to just causal discovery. And that was developed mostly by Wunger's group, but it was very underused, the causal inference and discovery specialists. Okay, so now how do we use causal graphs to improve statistical models? This is called causal machine learning. It's a very active field. It's a very recent field. Here we just showing one example where we discard the non-parents as predictors. And so the way we see that it works is you start by throwing all the predictors in. Here I'm showing the coefficient of determination, so up is better. And then here we go down to, we're predicting intensity at a 48-hour lead time. So it's in that case, it's a relatively easy task. And so when we throw all the predictors in the linear regression, it overfits. And so you get very good performance of the training set and bad performance on independent stores. That's expected. We have a baseline that's a long short-term memory network. So these are neural networks specialized in processing sequences. So they're particularly adapted to time series prediction problems. And we believe that's a pretty good baseline. But what's really nice is we considered so many predictors that if we use a causal discovery algorithm by selecting the right predictor, even though it's just a linear model, you can outperform this neural network. And so you get this classical shape on the training set where the more predictors you have, the more information you have, so the better you're going to do. But of course, that comes at a cost. You overfit eventually. And so we have this shape on the validation set where it goes up and then it goes down. And we can really test that causal feature, we call it causal feature selection to select the predictor works, is if it goes up very quickly at the beginning and then it goes down, because then it tells you that the most stringent causal discovery algorithm can really select the most informative predictors. So all the informative predictors are on the left here. So the first one that was selected by the causal discovery algorithm are truly the most informative. And then if you add more, then you lack generalizability. So that's what tells us that the methodology is working. And we check that it outperformed, in this case, other ways of selecting features. So the really naive baseline would be to select them randomly, or using lagged Pearson correlation where the lag is equal to the lead time, or you can be more sophisticated and use a random forest, and then in that case, we show that our method is slightly better. I'm not going to spend too much time on saying how we're currently working with the Sierra team, so Mark DeMaria, Kate Musgrave, and Mary McGraw, on improving shifts. So we want to inform the ship's developers on which predictors to potentially add they had never thought about. And we have this kitchen sink approach where you can test hundreds of predictors. And so we're working with the ship's data set, and I don't have time to go into too much detail. We have a whole replication pipeline where we replicate some of the predictors with RF5, and then that allows us to suggest new predictors. So these were 3 predictors that were suggested earlier this year. We've changed it a little bit to better adapt to the ship's vertical levels. And then we really want to go all the way to testing. And so what we do is we really send the predictors that we think are most causally related to Mark and Kate. And once they have them, they'll be able to objectively test them on real-time cases. And then we know that these machine learning methods can actually help with decision-making at the end of the day. Okay, that was for the causal part. I hope I convinced you that if you have knowledge of the underlying causal graph, which is not trivial, it can be physical knowledge sometimes, you can use it to constrain your regression algorithm, your statistical modeling algorithms in creative and constructive ways. And then I'll hand it over to Milton.
Hi. So I'm aware we're getting close to lunchtime. I'll try not to bore you and to keep you hopefully slightly awake. So first of all, I want to start out by thanking my collaborators. Without them, nothing of this works, right? It's a group effort. And one of the first things that I want to mention is you may have heard of artificial intelligence being used for numerical weather prediction, right? And there's been a lot of interest in artificial intelligence, especially as these larger models have come out. You may be familiar with, for example, Forecast NV2, which was developed by NVIDIA. You might be familiar with GraphCast, which was developed by Google. Plan Weather, which was developed by Huawei, which was the first one that came out of all these that you see. And also, quite recently, the ECMWF has also put out AIFS.
Importantly, you have different approaches in each one of these models. For CastNet-V2, they do spherical neural operators. For GraphCast, what they do is they rely on interaction graph neural networks. And PancaWeather uses transformers, and AFS makes a combination of the approaches by GraphCast and PancaWeather. But to all this, what do these models actually do? Well, for GraphCast, what they're talking about is if I grab the representation of the state of the atmosphere and I map it onto a latent space, can I evolve this latent space and then with a graph neural network and transform it back into the state of the atmosphere? For forecast NP2 is.
Oh, I have no battery. But I think the outlet is not. It's probably not working.
Try yes. Try one. No, this one doesn't work. This.
No,
it's okay. That's easy to solve at least.
This is all, and if the battery dies, well, presentation's over. I mean, lunchtime. But yes, for forecast NV2, what you're trying to do is learn a grid invariant filter in order to try to use that information in the Fourier space in order to make a better prediction of the next state of the atmosphere. And in PancaWeather, what it does is takes an approach that was developed for large language models. And part of it is trying to find a query key and value representation of the data. And we can talk about that later if you want. But ultimately, it just gives you the state of the atmosphere out of the point. Now, we know that the RMSE on the fields produced is low because of what we're trained on to do, but we're ultimately interested not only in the fields that it outputs, but some more, shall we call it, complex fields. In our case, we know that convection is important for tropical cyclones, right? And we know that because these models are trained on error 5 and output at similar resolutions, then you're not going to get convection resolved, right? However, you can get an idea of the information of a convective environment by being able to calculate, for example, CAPE. And our network collaborators and Michael Feldman found that they do a pretty good job of, like, if you calculate CAPE from the fields output by models, you get a pretty decent amount of information that you're able to use. And you can look at the paper if you're interested in, but ultimately what we find is that they do well on RMSE, which is what you expect, that we're trained to reduce RMSE. There's a little bit more of a disparity between looking at the outputs or the CAPE calculated from the outputs of these models when you start looking at the comparison with HRS, when you look at bias and some other metrics. So the question then becomes, can we post-process? Yes. So can we post-process the outputs of these neural weather models in order to be able to get a better prediction of tropical cyclone intensity? Well, in order to do that, we propose a very simple framework. We're going to grab the induction conditions from error 5. We're going to evolve it using the neural weather model. We're going to grab at the initial time the position of the tropical cyclone, and you're going to clip these fields that you generate at plus minus 30 degrees around that point. The reason for that being is that we know that tracks and error 5 are not necessarily going to be something that you're going to look at, but comparatively 1-to-1 when you look at IV tracks, right? And so we're just trying to see, can we actually get any information out of this as a first step? And so we're just going to use this larger box, and that doesn't give my algorithm any information about what I expect the track to be. And this is what happens when you do that for Dorian, right? And you can see the evolution of the MSLP field and the wind field in the forecast made by the AI weather model, so the neural weather model, in this case, PancaWeather. And you can see the storm like evolving in the forecast time. So it does kind of a good job. But we're not only interested about looking at, does the graph look pretty? We actually want to know, can we get some information from these fields? And preliminary results, yes. the person that we did was grab this clipped region, just look at the maximum wind in the outputs and the minimum sea level pressure in the outputs, and say, okay, just calculate out this entire clipped region and combine it with multiple linear regression in order to try to get a post-processing of the outputs. And you find that it has some scale compared to persistence, right? And the good thing about this is that we see that the information that you're getting from the model is giving you the kind of behavior that you would expect, and that it's a lot harder for it to beat it at persistence, to beat persistence at a very short time scale, but the information that you get allows you to get better prediction as your lead time increases. Now, this obviously doesn't, because it's a multiple linear regression that just looks at a reduction of the information that you had in those spatial fields. This doesn't take into account the spatial information, right? You don't see any of the structures, you don't see the things that we might find more interesting. So let's go ahead and train a convolutional neural network. And what you find is that we can overfit the intensities. Now, rather unfortunately, this means, because it's still a work in progress, very preliminary results, I still need to find a way to get that bit to actually generalize well to the validation data set. But at least for now, things look promising. And with that, I just want to leave my conclusions here. The neural weather models provide a cheap way and fast way to try to get a prediction of the outputs. We are able to get some information from the neural weather models that you can post-process in order to get a better prediction of tropical cyclone intensity, and the spatial nature of the neural network outputs can be exploited to a certain degree. So now back to Tom.
Okay, thank you, Milton. And what's really incredible with this project is that now you can get really nice and fast prediction at lead times of, let's say, a week of the entire global state of the atmosphere, which is so much more information that we're able to get just 2 years ago. And to finish, I think a lot of these, I think Frederick and Milton worked really, really hard, and you can see the results, but a lot of the results that are not, the work that is not shown is all the data processing work that was in it. And so, Maria will talk about it this afternoon, but most of the machine learning work is just pre-processing and cleaning the data. And so that's why we think benchmark data sets with accessible open data, open evaluation protocols, for which that's where the tropical meteorology community has to come in and really design evaluation metrics that when statistical modelists come in are faithful to what the community needs. We really think benchmark data sets are central to scientific progress. And as a proof, benchmark data sets have really accelerated progress in computer vision. That's why we've become so good at image segmentation, classification, etc. And they've benefited the community. So these global data-driven weather models, I would say, have really been bolstered by the creation of just WeatherBench. And it's one benchmark data set. It's very, very well done. Stephen Rath and others launched the ideas using Area 5 data, but just Area 5 data with the right evaluation metrics, with open data and clear protocol, launched a series of papers that now resulted in models that are competitive or beat IFS high resolution and deterministic forecast, but run on one GPU, which is something we would have never dreamt of just like a couple of years ago. And so we think we could unlock similar progress if we could come up with a good benchmark for tropical cyclone, and we've been really thinking about it for now more than a year. I think Susanna is currently in the project, but we want to open it to the entire community. So I'm going to send several links on Slack, and there's 2 ways you can participate. There's one overarching brainstorming document. So that's a Google Docs. That's something that a lot of people participated in, and so people have suggested climate data sets on climate timescale, race data sets, etc. I think what I've been most impressed by in this workshop is the number of amazing simulation output on tropical cyclone and a changing climate. I think if we put some of the simulations we've seen this week together, that's a lot of data to learn new relationships from that we didn't have before. Now, to submit to machine learning conferences, we have to be focused. And so what we've identified as a first step is short and medium range weather forecasting with post-processing of neural weather model, because that's a very well-defined problem that machine learners tend to be interested in. So I'll also share how to participate in that draft if you're more interested in participating in that. That's more of a short-term submission that we're hoping to submit to NeurIPS next year. So I'll send both of these documents, and then if you're more interested in learning about machine learning, we have the tutorials this afternoon with Maria, and I'll leave this slide up. But for me, one of the main messages I usually try to communicate is machine learning is not just a black boxy way of minimizing error. It's just a framework to be rigorous with the data. So if you're going to be rigorous with the theory, you may as well be rigorous with the data. And there's so much you can learn. Both you can generate new scientific hypotheses, you can design prediction schemes you would have never dreamt of. And I really think it's being underused, and it cannot be well used if the community is not actively informing statistical models about what matters. And so I really hope I convince you there's still a lot to do. The future is exciting, both in terms of physical understanding and forecasting and even longer timescales predictions. Yeah, thank you.
Thank you, Tom and Milton and Frederick. Questions?
Great talk. So I have a question about the neural weather model of post-processing. So I guess the most model we use are just deterministic, trained with the mean square error, I guess. But I guess like for a very long time, they just give you very blurry long-term like time topology. And we try to use like a probabilistic forecasting models, like, so that you can get more like a realistic outputs for the post-processing.
So as far as the neural weather models, people are working on probabilistic models. On our end, we are also looking at using a probabilistic version of the post-processing model. So not just having a single value that's deterministic. We're ultimately not terribly interested in. We want to see those nice little bars to give us our certainties. That isn't very much in the works, but this is truly like work in progress. So a couple weeks. I mean, it should in theory just like hit the buttons and run on GPU.
But Louis has results where you can, instead of just regressing the conditional mean, you regress there's many ways of doing distributional regression, right? But the easiest one is to regress the condition to target the conditional parameters of a prescribed distribution, normal, or you can be more sophisticated for certain variables. And so we have prototypes that work. And then Jen asked, other models are coming that will, yeah.
Very interesting work. I was wondering if you have thought about a combined causal discovery approach with a large like global data-driven weather prediction models. If you consider like Penguin or other models, the input variables they use to train the model actually are very limited, either in number of variables or the number of the vertical levels which we choose. Can we do a better job in like input variable selection? You can do this like across different timescales. I would think like on the longer timescales, if you consider some seasonal prediction, the input variables or the number of the choice of the vertical levels can be very different for the shorter timescale.
That's an excellent question, and there's several ways to answer it. I think what's tricky with machine learning is depending on the type of models you use. If you use a very simple model, then typically you need a lot of predictors. In that case, I think causal discovery can yield immediate benefits. Because then if you have a lot of predictors, some of them will lead to very poor generalizability. I gave a fun example before, we can think of many others in the atmosphere. Now it's a lot more challenging for deep learning models because these models use less variables, but they leverage an entire spatial temporal field. So for example, CNNs are a good example. They can have several channels, but usually it's not that many. So they don't use that many meteorological variables. They just use the entire spatial connectivity of these fields to extract information that allow you to make accurate predictions. So in that case, I think it's a lot trickier to think about the kind of causal feature selection that we've talked about, which is just restricting parents. Because then you're gonna, if you just have a couple of channels, you're gonna immediately lose crucial information, so you won't even be able to get a good fit on the training set. Now, there are many other ways of using the knowledge of the causal graph to constrain the output. So for example, if you know there's a collider structure, you can redesign your model to satisfy certain statistical conditions that you know are true. I've seen a thesis on that just like a couple of weeks ago, and it's quite easy to implement with any algorithm. So in that case, I think we would have to be a bit more creative than just selecting parents. Selecting parents is very good for simple algorithm with a lot of variables. That's good for. Does that answer your question?
Yes,
Okay.
thank you.
One more.
So yeah, so I have a question to Tom. So you mentioned in one of the last slides that there's a AI ready TC dataset on climate time scales. Can you elaborate a little more? I mean, the pace climate scale TC data, the formats and the regions.
So we don't have it for tropical cyclones. So just to clarify, for tropical cyclone, we don't have a dedicated machine learning benchmark dataset at this point. The closest we have is called TC Prime. That's developed by Sierra in collaboration with NOAA, and it has some notebook example, and it's very nice and easy to use. But I wouldn't say necessarily good. It doesn't. It's not AI ready in a way. It's ready for some AI applications, and it's really designed for NOAA type collaboration. So it's very good for that purpose. And we're collaborating with some of the people who are like TC Bench built upon TC Prime and other data sets to make it really easy to use for machine learners. Now, in terms of climate timescale benchmark data sets, they're a really good one, but they're not specialized to TC. So there's Climate Bench for climate model emulation, and there's ClimSim for climate model parameterization. These are, in my opinion, some of the best ones. But there's just so much to do. And the incredible thing is currently we have the Kaggle competition open for ClimSim, which is a benchmark dataset for machine learning based parameterizations. And you know, people come up with solutions you would have never thought of. And all the code is open source. And the top 10, 20 models, I mean, there's thousands and thousands and thousands of brilliant statisticians and machine learning experts out there that could really propulse the field years forward. But we have to frame the problem in a way that can help us. So it's really important that we define the evaluation metrics, the cross-validation protocols, etc., to make sure that it's relevant and useful, because it'll just minimize whatever you give them. Yeah.
All right, let's thank all our speakers again. Bon appetit.
So the new people have to go upstairs, get a ticket to go to the cafeteria.
Follow us.
Yes,
and we have to start at one the discussion, so we have to go now.
Wait till the ML portal is after?
Yes, then machine learning for after.
Okay. Good.